moving on. Moving on. We're going to start to build a transformer now. A transformer. So let's see this. We're going to use that inner solenoid now, and we're going to stick it in the outer solenoid. The current from our function generator will be going into the outer one. And all we're going to put on the inner one is just a channel 1 to monitor what's going on. And because there'll be a changing magnetic flux inside of this outer one, it will induce a current in the inner one, a voltage. All right, so by considering the two electromotive forces that are induced, we find the ideal transformer equation. So let's take a closer look. So the voltage we find in the inner one over the voltage of the outer one, that should equal the number of turns in the inner one divided by the number of turns in the outer one. A surprisingly simple equation, but with very, very useful consequences for us. Look, so if the number of inner turns is greater than the number of outer turns, that means the voltage of the inner one is greater than the voltage of the outer one. This is called a step-down transformer. That's what we have today. On the other hand, if the number of turns of the outer one was greater than the number of turns of the inner one, well, then the voltages would be opposite too. The voltage of the outer one would be greater than the voltage of the inner one. That's a step-up transformer. So what does this mean, step up and step down? How does this help us? Well, consider that the voltage that's supplied by the power company is much, much higher than the voltage you need in your apartment or home, like for your toys and your hair dryers and your computers. Well, somewhere along the way, that voltage needed to have been stepped down to what you need. And that's done in a transformer. Yeah, if you go out and you look at those telephone poles, power lines, and there'll be like little cylindrical boxes on top. Those are transformers, and they're stepping down your voltage. Cool. Okay, so after we stick the inner one and the outer one, well, we're going to find a ratio of the voltages at different frequencies. And this is how we're going to graph them. So while we're here, the outer voltage, that's still going to be measured with channel 2. The inner one, we're going to put channel 1 on there. And then we're going to find them at different frequencies. And we're going to find them at frequencies of multiples of 10. So it makes a lot of sense to make this a semi-log graph. In other words, the log of 10 hertz would be 1, log of 100 would be 2, log of 1,000 would be 3. It makes our graph simpler. And this is what it should look like. So this is what the point curve should approximately look like without the core inside, without the iron core. And then this one will be with the core. So you'll find the series of frequencies, the ratio of voltages at different frequencies with and without the core. And notice something else, that as the frequency starts to get higher, the dependence on the iron core starts to go away. Interesting. Okay, let's go back. Let's start to see here. All right, so now put this, bring it to 20 to anticipate. I'm going to start over. All right, but before I start using this again, I can't let this go. I have to show you something else. I'm going to put 12 volts of direct current through, just to see what happens. Can we induce an EMF without alternating current? Is this alternating current stuff a myth? Let's find out. So let's see here. So I just want to put this through the outer one. And now look. I go DCV. Okay, approximately 12 volts. Great. So now, Okay, so there's 12 volts going through this. And so now I'm going to put the voltmeter on the solenoid. And let's see what happens. Let's see, so now no voltage. No voltage. Nothing happened with the direct current. Let's try alternating current. Okay, so now I'm taking the function generator out of channel 1. Putting together my circuit again. So now into the resistor, the connecting wire to the solenoid, and then back to ground. Channel 2 across the solenoid. High end, low end. All right, terrific. Now channel 1 is going across the inner solenoid. Okay, so now let's look. All I have, notice there's no function generator, there's no battery, there's no EMF going into this inner solenoid. All I'm going to do is put this inside of this changing magnetic flux. And let's see if we get a voltage. So I'm just going to look at channel 1. Oh, that's so cool. A voltage is induced. Wow. All right, so now the rest is just gathering data. So for example, at 10K, we want to find the voltage of the outer and then the voltage of the inner, and then put the iron core in, find the voltage of the inner and the voltage of the outer again for different frequencies. So starting at 10 hertz and then moving up. Now, finding these at 10 hertz is hard. It might be too hard. You might not be able to do them, especially without the iron core. Okay, so then you find it for 10, 100, 1K, 10K, 100K. And then, last but not least, after you find those and you plot your graph, time to play again. Again, with the different waves, and you start sweeping different frequencies. And again, you'll find a resonance frequency. So, it's a little bit more complicated this time, because it's not just one self-induction. There's now mutual induction, because this is a transformer. So what do you stick into the L into the C for to calculate the theoretical resonance? Well, I'll give you some hints. You are given both the inductance and the capacitance of the outer one and the inductance and the capacitance of the inner one. But what you'll find is that the inductance and capacitance of this one are much, much bigger than this one. So it's like adding a raindrop to an ocean. It's still an ocean. And if you played before, like I recommended, you'll see that the resonance frequency you have is close to what you might get again. And I recommend, why don't you calculate the resonance frequency of this and see if it's even possible to get it. There you go. Faraday's law. Good job. Farewell.